Okay, so we're given the difference between these 2 years in temperatures. We're told that there are 51 different locations that we're sampling from, and X bar diff is 1.1. They tell us that the standard deviation is 4.9 degrees. So you can kind of see that there's only one standard deviation. It must mean that we're using this diff. We said a little bit about that on the lecture. So finding 90% confidence interval for this, again, we just have our point estimate plus or minus z star of alpha over 2 times the standard error of our point estimate. So our point estimate here is our x bar diff. Our z star of alpha over 2, using this 90% confidence interval, again, what we're really saying is our alpha is 0.1 because it's 1 minus 0.9. So you could use 0.1 divided by 2. Alpha over 2 is going to be 0.05. And so once you use your table to look this value up, we find 0.05 going to give us 1.645. Of course, you can choose to round this up. It's halfway between 1.64 and halfway between 1.65. So we just use 1.645. The standard error here is just going to be, remember, for x bar diff, this is really your standard deviation over the square root of n. So filling all this stuff in, x bar diff we found was 1.1 plus or minus 1.645. The standard deviation we found was 4.9, all divided by the square root of 51 here in this case. Let's go ahead and see what that gives us. 4.9 divided by square root of 51, and then times 1.645. We do get 1.1287 plus or minus, or I'm sorry, 1.1 plus or minus 1.1287. So I believe this question asks you for the lower bound. So we do 1.1 minus that value. The lower bound is negative 0.0287. And what about the upper bound? 1.1 plus 1.287. Okay, 1.1 plus 1.1287. So this would be the lower bound for this question, and for the next question, it's going to be the upper bound of 2.287. So normally we give the confidence interval in this kind of form, but since it's difficult to ask this format in there, I just tell you to go ahead and put this in for the lower bound. That's one of the questions. Put this in for the upper bound. That's the second question. That's question number 2. We're told to find the test statistic between this before and after. We would like to see if there's a significant decrease. So they're asking us, can we conclude that there's a decrease? So of course, in this case, our HO and our HA, we can write these. The first things first, we want to compare these means. But we see that we do have 2 standard deviations. So rather than using x bar diff, what we're doing instead is simply subtracting the x bars, where this is after minus x bar of before. So this would kind of be the idea for the setup. However, we don't want to use our point estimates. Recall, for the actual hypotheses, we do want to use the population parameters. So we would have mu after minus mu before. So this could equal 0. Equaling 0, of course, indicates that they're not different, right? And of course, if there is a significant decrease, so if it's decrease, when I do after minus before, if after is actually small, then when I subtract this to be decrease, to be less than 0. So this is the hypothesis setup. Now, of course, we want to find our test statistic. So our test statistic is just going to be our observed, or I guess our point estimate, minus our null value, all over the standard error of our point estimate. So our point estimate here is actually x bar after minus x bar before, which is given to us in the problem. It's going to be 9.6 minus the before is 10.5. And then off to the side, minus the null value. The null value here, we go to our null hypothesis, it's 0. So I put in 0. It's just the value that's on the right side here in the null hypothesis. This is all going to be over the standard error for the point estimate. And this one gets a little bit more complicated. If you recall, this is our point estimate here. So the standard error for this thing is just the square root. Looks a little ugly. The standard deviation squared for after, all over the square root of n after, plus the standard deviation squared for before, divided by the square root of n before, how many we had before. So we can go ahead and put these things together. Continuing on, 9.6 minus 10.5 is going to give us negative 0.9 on the top. Is that right? Yeah, negative 0.9 on the top. And on the bottom, filling this stuff in, I have the square root of s squared after. This is going to be 2 squared. 2 squared gives us 4, all over the square root of n, the square root of 65, plus s squared before. We have 2.2. When we square that, we get 4.84. All divided by the square root of how many were in that sample? 60. So the square root of 60. Or I'm sorry, there's actually, so let me make a correction here. I'm sorry, there is no square root here. So sorry, it's just s squared after over n after plus s squared before over n before. So it's just going to be 4 over 65, so 2 squared over 65, and plus 2.2 squared, which is 4.84, all over 60. And we'll take the square root of this whole thing. So this gives us 4 divided by 65, gives us 0.061, plus 4.84 divided by 60. All this gives us, let me write this on a different paper, negative 0.9 all over the square root of, or I'm sorry, this becomes negative 0.9 all over the square root of 0.1422. Taking the square root of this thing, I get negative 0.9 all over 0.3771, which ultimately gives me negative 2.387. Now, of course, to look this up in the table, we're going to have to round this to the nearest hundred. So we would use negative 2.39. If for some reason you went ahead and set your hypothesis up as before minus after, this would flip, and as it turns out, you would get a positive 2.39, which would also be correct. Let's go ahead and carry on with the next question. The next question says, can we use this test statistic to find the p-value? So can we use this test statistic to find the p-value? Now, remember what's happening here. We got this sort of thing going on with a 0 in the middle. 1, 2, 3. So somewhere our test statistic is here. We're interested in finding this area. Why is it not on the other side? We go back to our original hypothesis. We were just looking to see if there was a decrease. If you look at the wording of the problem, it says decrease. It tells us it's one-sided. Again, if I had not equal, then I'd have this other tail. But it's just the one side there. And furthermore, our table of values does give this to us. So looking up negative 2.39 in our table, we get negative 2.3.0084. So our p-value is 0.0084. Of a sample of 200, we found 40 smoke. So we'd like to go ahead and extend this to find a confidence interval for the true population proportion. So the way we do this, again, the confidence interval is not any different. It's just point estimate plus or minus z star of alpha over 2 times the standard error of our point estimate. This time, however, our point estimate is going to be, we're looking for a proportion that tells us it's going to be p. So if you want your test statistic, or I'm sorry, not your test statistic, your point estimate is p hat, which approximates p. So filling this stuff in, what do we get? We're interested in p hat, our point estimate, plus or minus z star alpha over 2. And our point estimate standard error for this thing is going to be the square root of p times q all over n. So let's go ahead and see what we're given. Or I should say p hat, q hat. P hat, recall, is just a simple fraction. What we're interested in over the total. So we're interested in who smokes. It's going to be 40. Over the total here is 200. So this x over n. X over n, if you prefer. This reduces, of course, should give us 0.2. So p hat is 0.2. So we can use that to find q hat. It's going to be 1 minus 0.2, or 0.8. So let's go ahead and plug all this stuff in. P hat was 0.2, plus or minus z star of alpha over 2. For 95% by now, we know that it's 1.96. And if we're not sure, you can of course do the same thing that we did in the past problem, where we use the alpha is 1 minus 0.95, so alpha is 0.05. take half of it, find in our table. We find it's 1.96. And our standard error here is going to be 0.2 times 0.8, all divided by n, which here is 200. How many we have in total? So 0.2 times 0.8 gives us 0.16 divided by 200. See what we get. Now, if you do type this into your calculator, suppose before you go ahead and take the square root, you type all this in. Suppose you get 8e to the negative 4. If you haven't seen this before, what this really means is 8 times 10 to the negative 4. Your calculator is trying to save space. So in essence, this is really just an 8 here, and there's a 4 here. It's really telling you there's 3 zeros. So this would be the square root of 0.0008. You have not seen that before. So it's not 8. Don't use 8 in here. Do know that this is just scientific notation. Your calculator is trying to save digits and bytes. 8 times 10 to the negative 4. If you do know how to convert this, you shift the decimal to the left 4 units. Or it's simple enough just to know that we use one less zero than whatever this is. So continuing on, take the square root of that thing. We get 0.028. So this is 0.2 plus or minus 1.96 times 0.028 to 8, about something like that. And so ultimately what we get, or almost ultimately, 0.2 plus or minus 0.0554 once I multiply these two values together. And so the lower bound is going to be 0.2 minus this value. And that will give us 0.1445, or I guess 1.446. The upper bound is going to be 0.2 plus this, which is going to give us 0.2554. So again, for these confidence intervals, I ask you two questions. I say find the lower bound, the smaller one where we subtract. The upper bound is the second value.